Okay, so we're going to start talking about forces between charged particles, electrostatic forces, so what we know is that from observation, so everything that we know about electromagnetism comes from a series of observations that Coulomb and his buddies made back in the day. So if you have particles that can have two different signs of charge, positive and negative, we decided to call it. We could have called it red and blue if we wanted to, but positive and negative. And if they have the same sign of charge, or they're like charged particles, like protons, they repel one another, and they both experience the same magnitude of force of repulsion. And if I have two particles with opposite sign of charge, take a proton and an electron, they tend to attract each other. Okay, and so experiments were done in the laboratory to measure these interactions, and I'll demonstrate some of them, the types of experiments that were done in class on Monday. And through those experiments, now they weren't experimenting at the time with protons and electrons. They were experimenting with objects that were much larger that were charged, like pith balls, for example. It was determined that the force between charged objects is proportional to, that's the alpha thing, the amount of charge that each object carries, okay, multiplied together, and inversely proportional to the square of the distance between the two particles, which I'll call R12. Okay. All right, so this is the inverse square law for electrostatic forces. Now, we've seen inverse square laws before, and the last time we talked about inverse square laws was when we were talking about sound waves. So you take a point source of sound, and it emits a certain amount of energy and a certain amount of power, and as those waves spread out in space, the intensity of the waves drops with 1 over r squared. And we understood that to be a spreading of the energy in space. That's what caused that to happen. Now, it turns out our current understanding of how electrostatic forces work is not, that same argument applies in explaining why you get a 1 over r squared dependence for the force. Now we think about fundamental forces like electric forces to be due to particle exchange. So what you can think about, and I'll be very fast and loose in my explanation here, but you can think about one proton sitting in space throwing photons in all directions. The particle, the boson that is associated with the electromagnetic force is the photon, and we consider that particle, the photon, to be the force carrier. Okay, and the reason for that, you can think about these two particles sitting in space. One of them is throwing photons in all directions, and those photons are spreading out over 4 pi r squared area as it moves out, and so the number of photons goes down as you move further away, and then those photons hit this other particle and are absorbed, and that causes the recoil or the motion. Okay, so, and then you can view it from the other point of view. The other particle on the right is also throwing photons in all directions and pushing on the particle to the left in the same way. So I'm, again, being very fast and loose. It's not really throwing photons in all directions. We think about them as virtual photons, but that idea, you can think about it underlying why you get 1 over r squared. And I'll say that again in class and talk more about it. Okay. But anyway, we have this 1 over r squared behavior. Now let me write down things a little more formally. So if I have particle 1 sitting here, particle 2 sitting here, and what I'll do is pick an origin. You always get to pick the origin in the problem that you're working on. So we'll pick an origin over here for no good reason, just to pick one. And I'll label it with an O with a squiggly thing. And so the distance to particle 1, I can draw a vector locating particle 1 in this coordinate system, and I'll call that R1. I can draw a vector locating particle 2, and I'll call that R2. Okay. Now the force between these two particles can be written as the following. So F, it's a vector. Now it's going to be proportional to the charges, so Q1, Q2. Okay, and inversely proportional to the distance between the two. Now I need to be more careful here because I'm considering the force on one of these particles. Okay, Let's consider particle 1. So what I'm going to do is consider the force on particle 1 due to particle 2, which I'll write as F12. Okay. Now what I'm going to do is define a vector that points from the particle that's doing the forcing, and that's number 2, to the particle that's being affected, which is number 1. So what matters is how far away that particle is from particle 2. Particle 2 is the one that's is exerting the force on it, and the force that particle 2 exerts on particle 1 will depend on how far away particle 1 is. And so we call this vector here R12. Okay, and I'll give it a vector sign, and formally we can write that vector R12 is going to be R1, little r1, minus R2. Okay, so what I do is I flip this one around here. Subtracting a vector from another is the same as adding the reverse of it. Okay, so if I take R2 and reverse it, and then start here and go here, and then I'm going to put this tip to tail, and then I go here, you see that I trace out the vector R12. Okay, so it goes like the magnitude of R12, the length squared. Now, if I picked a particular unit system, I'd be done. I could pick a unit system where this describes the force, but in SI units, this is not the right way to go. If I use coulombs for the charge and meters for the distance, I have to multiply by another coefficient to get the units right, and the coefficient in SI is 4 pi times epsilon naught, or epsilon naught is the permittivity of free space. You've often, I'm sure, seen it written as K, Q1, Q2 over R squared. We will not do that here. K is the same as 1 over 4 pi epsilon naught. Okay, but now that you're out of high school, we don't use that anymore. We use 4 pi epsilon naught, and we'll see why later on, because epsilon naught will show up in other contexts. All right, so one last thing to say is that this is a vector, and so we need to give it a direction. So we've given it a magnitude. The direction is going to point, if both 2 and 1 are positive, or both are negative, the force will point along the direction of R12. And so that's the case where both of these are the same sign, and you get a positive value for this, what I've written down so far. Okay, so we just say it's going to point along the direction of R12, but we use the unit vector, okay, to describe that. Now the unit vector R12, when I put a hat on it, I mean unit vector, so a vector of length 1, so it adds nothing to the magnitude, but it tells you what direction it is. You can formally define it as R12 over the magnitude of R12. Okay, all right. Now another way, see if I can squeeze it in down here, noting this definition of R12, I can also write my force on particle 1 due to particle 2 as Q1 times Q2 over 4 pi epsilon naught R12 cubed now, because what I can do is instead of R hat, I can write R vector 1, 2, but then there's an R cubed. Now, it still scales as 1 over R squared, okay, because I have an R up here, and I have 3 R's down here, so it ends up being 1 over R squared in the end. This is just another way to write it if you like, okay? And you may see it written that way. Okay, let me do 2 things here before I quit on this video. The first is to just do a quick example of a vector R12. Now again, you can always pick the coordinate system that you like. Okay, so let's imagine I have 2 particles, and I'm going to pick my coordinate system so that one particle is sitting on the axis, which is always not always, but often a smart choice. That way it's just sitting at x equal to 0, y equal to 0, and the second particle is sitting somewhere x, y. Okay, and implicitly I'm assuming there's no z difference between the 2 particles. I'm setting z equal to 0 to be the plane where they both sit. So in this case, R1, little r1, the location of the first particle is 0. R2 is going to be x hat plus y hat. That's going to be the vector that points to the location of 2. This is R2 here. Okay. And so if I define now, if I want to know the force on particle 1 due to particle 2, I want to know the distance from 2 to 1, and that's going to be the opposite of R2. So it's going to be minus x, x hat, minus y, y hat. Okay, will be R12. And the magnitude of that vector, R12, will just be the square root of the squares of the components. Okay, hopefully not surprising. And therefore the unit vector, R12 hat, will be minus x, x hat, minus y, y hat, over square root of x squared plus y squared. Okay, and so if I write now my force down for this situation, the force of particle 1 sitting at the origin, minding its own business, due to particle 2, I can write it as Q1, Q2 over 4 pi epsilon naught. Now, in the denominator I have R12 magnitude squared, which is just x squared plus y squared. And then I can write the unit vector here, which will be minus x, x hat, minus y, y hat, over the square root of x squared plus y squared. Okay, pretty complicated, huh? But that's how you formally write down the mathematical expression for the force, both magnitude and direction. So if Q1 and Q2 have the same sign, then the direction of the force will be diagonally, down and to the left. If Q1 and Q2 have opposite signs, I'm going to get a minus sign from Q1 times Q2, and that will flip the sign of R12, and it'll go diagonally up and to the right will be the direction of the force. So that'll be attraction of 1, 2, 2. All right, let me squeeze in one more concept in this online lecture, and then I'll stop. And that concept is what happens if there's more than one particle, okay? And that's the concept of superposition. So this is the same word we use when talking about waves on a string. It turns out that the force of, if I have 3 particles, so one here, one here, one here, so here's 1, 2, 3, all I do is just add the forces as if the other particles weren't there, okay? So if I want to calculate the force on particle 1, what I'll do is I'll sum up all the forces of other particles, that basically force of on particle 1 due to the ith particle. So in this particular example, it would be F12 plus F13. Okay, and this just indicates the forces are linear, that you just add them up. Okay, it doesn't get amplified by the fact that there's another particle nearby trying to push on you too. They just push independently, and you just add up the total force. Okay, so that's the concept of superposition. So if I have a particle 1 that's sitting among a bunch of other particles that have charges, the force on particle 1 will be the sum over all the other particles, Q1, Qi, okay, where the ith particle sits at some point in space, which I can denote as with a vector R1I, okay, and then I have R1I hat. Okay. All right, so let me stop there.